If you're really on top, you can get ahead and get web design done. Yay! It's a new start, right? Okay, so we're going to talk about maximum and minimum values of functions. So some important applications of calculus are things called optimization problems. We're going to talk about those in section 4.7. But in these problems, you want to find the optimal or the best way of doing something. So, for example, suppose that your Coke, and you want to put 10 ounces in a can, right? That's something you say, I know my cans are going to be 10 ounces, right? The question you might want to ask is, what shape has minimum material for 10 ounces? Does that idea make sense? So is a tall, skinny-ish can like that okay, or is short, squat better? Like, what shape should that can be so that you use the minimum amount of aluminum possible, which kind of equates to minimizing the surface area. Does that make sense? Okay, or you could say, suppose you have, I don't know, fencing. You want to maximize the area enclosed by said fencing. And those problems you can actually often do with algebra 2 because they end up being just parabolas. But you could say, decide you want to make a fence for your chickens that looks something like this. And you have 100 yards of fencing, and you want to say, okay, how can I maximize the area? If I enclose the biggest area but still use my 100 yards of fencing, this actually, so you can find the best one. So those kinds of problems are things that we'll solve using these techniques. So they all boil down to finding a maximum or a minimum of a function. That's what we're going to do today, is find maximums and minimums of functions. And we'll talk more about how to find specific functions for complicated real-life situations later on. Okay, so first, some definitions. A function has an absolute maximum, which is also called a global maximum, at some point C, if the y value at that C is bigger than or equal to the y value everywhere else. It's like the absolute highest point in your world. So, like in the world, Mount Everest. Does that idea make sense? If the world is your whole world. If your world is Alaska, highest point is Denali, right? The mountain formerly known as Mount McKinley. The function has an absolute minimum or global min at C if the opposite is true, f of x. F of C is less than or equal to f of x for all x in the domain of f. And these things are called the extrema, the extreme values, extreme highest or extreme lowest. Extrema because plural, right? Pretty sure that's probably Latin, maybe. I'm math, I don't English. I don't Latin. Okay, so this picture I created on my computer, but I meant it to have closed dots there and there, like actually filled in dots. We can talk about how it would be different if there was open dots at those points. So find and label the absolute / global maximum and the absolute / global minimum. So which point is the highest?
That point there.
This point on the far right, that would be the absolute max. You technically should probably give an ordered pair. So it's, like 1.5-ish, comma, I don't know, 2.7 or something about like that. Like it's because I drew the picture that it's imperfect. Okay. Where's the absolute min?
Between -1 and -2.
Yeah, down there at that dip, that's the absolute min. And it has coordinates approximately, I don't know, like negative 1.6, negative 4.2-ish. I mean, approximately. Now, that's if I had those things as filled in circles, okay? Just because it'd be good to talk about, what if I would have had them as open circles? So what if they'd been open? So does the absolute min change if they'd been open circles? No, the absolute min is the same with open circles. But if there's an open circle up there, there's no absolute maximum. Because you can't find one point that's higher than all the others. You can get infinitely close to that little open circle, right? But you can't get all the way there.
Is it -1, -3?
What if your open circle was at -1, negative?
And just took out the rest of it. Then you'd have no.
Oh, I see.
Minimum
What
as
if the,
Just
so,
before, anywhere before the trough.
so like if I put like an open circle there,
Yeah,
you'd have no min and the rest of the picture is gone.
yeah.
Yeah, then you would have no min and no max. Sorry. You would have neither a min nor a max.
So you have to have either.
You have to have filled in circles, a trough, a something like that. Yeah.
Yeah.
So, for example, if I drew this picture, that has no absolute min, no absolute max. If I drew that picture, there's still an absolute min and an absolute max. Does that make sense?
Yeah.
Okay. So the point is open circles can't be highest or lowest. Also, something like that function on forever would have an absolute min but no maximum because it goes to infinity. Okay. Okay. So if you look at the picture that you had in the previous page, there are certain values who are the highest or lowest value around. These are called local extrema. So local maxima and local minima. So that picture looked something like this, right? Approximately-ish. All right, so a function has a, what's the word? It's called a relative maxima, or local max if f of c is bigger than f of x when x is close to c. So think about this as like if you were climbing this hill, what things would appear to be false summits? You see what I'm saying? Like, so this thing would appear to be a false summit in some sense, right? That number is called a local max. It's the highest point around. Does that make sense? It's a bump up. What are these other two going to be? Local mins. So they're called relative minima or local minima if f of c is less than or equal to f of x.
So would the one on the left have two names, local and?
Yes, this one would be local and global. And these local extrema, at least in this textbook, must be intermediary, like in your interval, not endpoints.
Now you have filled in dots on these.
I do have filled in dots on these, yep. But the
they were
point is that if they were open, it wouldn't change anything about the local behavior. So, but the kicker, and I think certain textbooks actually do say that endpoints can be local extrema. I mean, I think they define close in this textbook as an open interval, and so you can't make an open interval around a closed point, although with certain topology you can. So anyway, just in this textbook, local extrema don't happen at endpoints. Okay, just in the middle, that's the thing to remember. Because you could make it happen, but it's just quite technical, it's not really worth your time.
So if it was an endpoint, would it just be a global extreme?
If it's an endpoint, it is a candidate for a global extrema, but it doesn't have to be. Yep, like the right endpoint in that picture was a global extrema, but the left endpoint was not. Yep. Okay, so here's this function. Find the local and global maxima and minima, and once again, we're just gonna assume that those are actually filled in points. So where is the, first the global stuff, where's the global max? Far left, yep, there's the global max. Where's the global min?
3.
Yeah, 3. Okay, and then how about any local max or local min?
1.
Yeah.
Local max.
There's 1 for local max,
0 for local min.
0 for local min,
Right?
and this one's also a local min. Now remember that endpoints can't be local. Endpoints are only candidates for global stuff. They're not candidates for local stuff.
Could you just say the local max is at x equals 1?
Yes, you could. And the thing is, I mean, if your pictures are prettier than mine, you could say it's at, yeah. You could say global max at x equals -1, right? Global min at x equals 3. Yep. And I think that you'll have to give the WebAssign the values, but the point is, what does it look like in a picture? Okay. So the extreme value theorem says that if f is continuous on a closed interval, then f attains an absolute max and an absolute min somewhere on that interval. So as long as you're continuous, then this says you have a max and you have a min. Doesn't tell you where. Okay, so you have a couple options. The max and min could be at endpoints. Does that make sense? You could have something like this, for example, right? And the max happens on the right and the min happens on the left, yes? Now, because they said closed interval, you're not gonna have open endpoints, right? So that's not gonna be a problem. What else could possibly happen?
If it was like horizontal line.
Sure, if it was a horizontal line, the max and the min are the same thing and they happen everywhere. Does that make sense? That wasn't what I was thinking for my option 2, but sure. You could have one thing happening intermediary, right? Or you could have something like both the max and min happen intermediary, right? I drew that one curved on purpose. And if the function is, if the interval is not closed, this is not true, as in this theorem is not true. And if the function f of x is not continuous, this is also not true. Like you can't find a max or a min. So, for example, for the not continuous thing, you could have a function that looked like, let's say, that kind of thing, right?
No.
And that doesn't have a max because of the whole open circle thing.
Does that have a local?
It does have a local, yep, but no global max. And so that's what this theorem is saying, is you know you're gonna have is that these things are true. Okay, so that's the basic idea what this extreme theorem says. Now the question is, how are you going to find those maxes and mins assuming your function is continuous and they exist in the first place? So the pictures you drew on the last pages, the maximum or minimum can happen at an endpoint, that's a possibility, right? Or at a place between the endpoints. So between the endpoints looks something like this, and I drew that pointed picture on purpose. So if the max or minimum does occur somewhere in between the endpoints, what is the derivative at that point for the first picture? This one, f prime of x is gonna equal 0, right? Will the derivative be 0 at the maximums and minimums in the second one? But what's it gonna be? It's gonna be undefined. And it turns out if your maxima and minima happen within the interval, this is the two ways it's going to occur. Either the derivative is 0 at that point, or it's undefined at that point. You see the second one so often that you almost forget it, but you see the first one so often, you forget about the second one an awful lot, okay? So Fermat's theorem says that if f has a local max or min, and if the derivative exists, then the derivative is going to be equal to 0. Okay. Now, what it does not say, one thing. Would it be true that if the derivative is equal to 0, then, so we'll say at some x equals c, then f of x has a max or min at x equals c? Is that necessarily true? Could the derivative be 0 but not be a max or min? And it could. Here's an example. What if I gave you x cubed and we'll just say from -1 to 1. If you find the derivative, you get 3x squared. That's 0 at x equals 0, right? Is there a max or min at x equals 0? No, right? Then this is pretty obviously not, yes. So even if the derivative is 0, it might not be a max or a min. Okay? What it tells you if f prime of x equals 0 for some number, this might be a max or min. It doesn't guarantee it, but it says it's a possibility. It's like potential maxima and minima. And I kind of got ahead of myself because that's what the next example actually says. Is that, so like for this thing, the derivative is 3x squared, and this derivative is equal to 0 at x equals 0, but there is no max, min at that point. And this thing, this derivative is undefined at x equals 0, but that's min. Does that make sense? So the derivative being 0 tells you kind of like where you can start looking. But you've also got to watch out for the fact that they may not be max or mins at all, or the derivative could be undefined and that's a max or min. So those numbers where the derivative is either 0 or undefined are called critical numbers. That's the next thing we got here. So Fermat's theorem tells us where to start looking. Some potential x values for maxes and mins. It gives you a list of things that could be maxes and mins. Okay. So a critical number of a function f is a number in C in the domain such that either the derivative is 0 or the derivative at that point is undefined. And if you find critical numbers, you find potential maxes and mins. That's what you're looking for, things that could be maxes and mins. Okay. So find the critical numbers for these functions. So first thing you're going to do if you're going to figure out if the derivative is undefined or 0 is take the derivative in the first place, right? So what's the derivative for this function?
3x squared plus 2x minus 1.
Mm-hmm. And critical numbers refers to the x coordinate only. Okay, so set it equal to 0, it being the derivative. And if you hate factoring, you can always use the quadratic formula.
I hate that too.
Okay. Well, it's like saying if you hate beans, you can eat your peas. So can you factor this though? It's not that bad, is it? How do you make 3x squared?
3x and x.
3x and x. And then what do these last two numbers have to multiply to? Almost -1. So it's either 3x plus 1, x minus 1, or it's 3x minus 1, x plus 1. It's one of those two options, right? This is the second one. Yep.
It's the second one.
Well, I'm trying to make you think. That's because I'm choosing. But, okay. So then you have 0 equals 3x minus 1, 0 equals x plus 1. What are your two x's? 1/3 and -1. So two critical numbers. How about you find them for part B? Because it's really not that bad. This one's even easier factoring. Did anybody get critical numbers? Do you agree with my factoring? Did you take out the 3? Did you get x minus 2, x plus 4? So what are the critical numbers?
-4 and 2.
X equals -4 and x equals 2. Okay. What'd you do?
Did pull that 3 out. I
Yeah,
was like,
you should ask yourself, like,
Expect us to do it that fast? I'm like this.
you were trying to guess and check, and it's lots of possibilities, right? So yeah, moral of the story is always check for a greatest common factor, right?
Hate those guys.
You hate those guys? No, you love those guys, because those guys made the problem a lot easier, didn't they? Yep. Okay. Now, for this thing, you can use the product rule, or you can distribute and add exponents. I believe it's easier to distribute and add exponents. Do you agree? Before you take the derivative. So this is going to be x to the how many fifths? 9/5, yep. Minus 4x to the 4/5. This will be the first example where we have a derivative being undefined. Okay, so f prime of x is 9/5 x to the new power of
4/5.
4/5, lovely, minus 16/5 x to the new power of,
-1/5.
or 9x to the 4/5 over 5 minus 16 over 5x to the 1/5. And this is why I made you find common denominators, because you're going to need to for stuff like this. Okay. Is everyone okay with the derivative and all that part of it? Okay. What do you do to get a common denominator? What do you multiply the first ratio by?
X to the 1/5.
Mm-hmm. It actually works out quite nicely too, doesn't it? Like if you have x to the 4/5 times x to the 1/5, that's x to the 5/5, which is just x. So that's 0 equals 9x minus 16 over x to the 1/5. Yes, that. Mm-hmm. Okay, so we're solving that equal to 0 and also figuring out where it's undefined. So where is f prime of x undefined? At x equals 0. And you only count those points if the original function was defined there. By what I mean, could you have plugged 0 into the original function? Yeah, you could have done 0 to the 4/5 power, right? So that's a place where it's undefined. And then to solve it equal to 0, you just assume the denominator is not 0, multiply by it on both sides. You get 0 equals 9x minus 16. What's your other critical number? X equals 16 over 9. Okay. But you wouldn't call a number a critical number if the function wasn't defined at that point either. Does that make sense? Like if your function had been 1 over x, 0 is not a critical number because you can't plug 0 into the original function either. Now, some critical numbers you recognize by knowing what the picture looks like. We don't have a formula for differentiating root x, or absolute value x minus 4. But can you graph that function and tell me where the critical number is? It's a V shape shifted. I think it's shifted to the right 4, is that correct?
Yep.
Yeah. So it's like that. So where is the critical number? At x equals 4. Yep. So you don't actually have to do any calculus. You can just say, okay, absolute value is a V, and if the point happens at this place, that's where the derivative is undefined, right? And so because f prime is undefined at x equals 4, right? Let's add in a c that's a little bit different. What if I gave you g of x equaled, we'll say, absolute value 3x minus 2. Because you don't graph stuff like that quite as often, right? Yes?
Right, what does the little c end in?
Oh, critical number. Yeah, no problem. I'll make abbreviations. Okay. Why is this next one that I wrote on there not an obvious shift? Because the derivative is 13? What?
Oh.
That's an, I'm sorry, that's an absolute value bar. It does look like a 1. No, my bad. It's not obvious. Yep. Okay, so it's an absolute value bar. The reason is there's a 3 in there with that x. Does that make sense? So how you can handle that lots of ways, but here's my way. Take out a 3. Do you buy that that's the same thing? Does that make sense? Take out a greatest common factor of 3. This is clever. That's what I'm here for, teaching you clever. 3 absolute value, x minus 2/3, right? That's same thing, yes? What's this 3 gonna do to your v?
Stretch.
It's gonna make it steeper. It'd be widened if it was like a 1/3 or something. So it's gonna be some steeper thing shifted over how much? Over to 2/3. And the steepness of the v really doesn't matter for you guys, right? It just matters where that point is. Does that make sense? So this thing would have a critical number at x equals 2/3. So that's how you can deal with it if it's a little bit more complicated. Factor out the stuff from the absolute value bars and then shift from there. Okay. So now we're going to actually find maxima and minima. All right, so this is something called the closed interval method. So to find the absolute maximum minimum values of a continuous function on a closed interval, the first thing you do is you find the critical numbers. So where f prime of x is 0/undefined. And then you want to find the absolute biggest, or like the absolute highest or the absolute lowest on that interval. Which means if you're going to find the absolute highest or absolute lowest, you've got to find the y's. So plug the critical numbers into F, like the original. That finds you all the y values at the critical numbers. Where else could the maxes and mins have happened? In those pictures we drew, they happened in the middle or they happened at the endpoints. Now you also need to plug endpoints into F. And I guess this is kind of like step 4. The largest y value is the max. Smallest is the minimum. And the kicker is that it wants y values. If WebAssign says, or the homework says, find the absolute maximum, it's asking for the y. The x tells you where it is, the y tells you how high up or down it actually is. Does that make sense? They might ask for stuff as an ordered pair, in which case you give both coordinates, right? But like when I taught AP Calc, one thing that was tricky is that they had these multiple choice questions that said, find the maximum. And the students would find the x, and that was the wrong answer, and it was listed there as a possibility. Because tricky. Tricky. Evil multiple choice test. And one more thing to watch out for. Make sure your critical numbers are in your interval. That might seem sort of silly, but I mean, you could have the derivative being 0 somewhere outside the interval you've been given. So just make sure that when you find them, they must be in between A and B. And if one happens to be an endpoint, lucky ducky, you only have to test it once.
Clear as mud.
Clear as mud. Really? Mud?
No.
Silty water. Okay, so let's actually do it. Find the absolute max and min of this function on the given interval. Okay, so first thing is find the critical numbers. So the derivative is equal to what? Great. Set it equal to 0 and solve away. Solve your little hearts out. So 3x plus 1, x minus 1. So x equals positive 1, negative 1. And I kind of gave that last warning on purpose. Are these both in your interval? No. Which one is in the interval? 1. So negative 1, not in interval, so does not count. And steps 2 and 3 can be put together. So plug in your endpoints, plug in your critical number. Find f of 1. Find f of 0. Find f of 3. Okay, that will tell you the y values at those points. The biggest y value is your max, and the smallest y value is your min. So when you plug 1 into the function, you get 1 cubed minus 3 plus 1. I think that's negative 1. When you plug in 0, what do you get? And when you plug in 3, you get 27 minus 9 plus 1. So the absolute max is f of 3 equals 19. And the absolute min is what? And that kind of is the best way to give it because it tells you both the x coordinate and the y coordinate in the same go. Does that make sense? Or you can say an ordered pair. You could also have said 3 comma 19, 1 comma negative 1. Same thing, right? You agree not super hard, right? Okay.
It's not asking for order pairs, could you say 19 and negative?
You can just say 19 and negative 1. Yep.
Real quick, where'd the F of 3 come from?
That was an endpoint. So you could, exactly. Yes.
So the numbers that you choose to plug in X, that's,
Say that again.
how do you know, how do you like choose the numbers that you plug in?
You plug in the critical numbers.
No, I mean, like when you did F1, F0, F3.
Yeah, I know.
Oh,
You plug in the critical numbers, like f of 1. 1 is a critical number.
okay.
What are the and what's the 0 and 3? Where do they come from?
Oh,
So what are those? They're the endpoints. Just like the directions said, like on the last slide, you plug in the critical numbers and the endpoints. So if our interval would have been like -2 to 3, we would have also plugged in -1. Okay, trick, just because. So find the derivative. What is the derivative?
1 plus 2 sine of x.
It'd be 1 plus 2 sine of x. You have a double negative canceling out that negative, right? Set it equal to 0. 1 plus 2 sine x. We're looking for where sine x is -1/2. So that's quadrants 3 and quadrants 4, right? Okay, is it 7 pi 6 and 11 pi 6, or is it the pi thirds, 4 pi thirds, and 5 pi thirds?
The first one you said,
The first ones I said, yeah, x equals 7 pi 6,
you can see where it's halfway down the,
and x equals 11 pi 6, right? A sixth past. Okay, good. So those are your critical numbers. And you're gonna have to plug these and the endpoints into your original. Okay? So who do you want to do first? Critical? Sure. We'll do f of 7 pi 6. So that's going to equal. So when you plug that in, it goes in for all the x's, right? So it'll be 7 pi 6 minus 2 times cosine of 7 pi 6. Okay, so 7 pi 6 is this guy, right? Mm-hmm. And it's, I believe it's negative root 3 over 2. So -2 times negative root 3 over 2. So that's 7 pi 6 plus root 3, right? Does that make sense? Okay, let's do 11 pi 6.
that's just how you do
You might have to get a calculator to estimate it, but you know, for now, it's what we're going to leave it as. If WebAssign didn't ask for a rounded answer, it's going to want that answer anyway, so we'll just leave it like that for now.
so that's our y, right there.
That's your y, yep. Your y is what you get when you plug in your x, right? It just happens to be a disgusting y. 11 pi 6 will be 11 pi over 6 minus 2 cosine 11 pi over 6. And the only difference there is that instead of being negative root 3 over 2, it's positive root 3 over 2. Does that make sense? So that's 11 pi over 6 minus root 3. Okay. And then how about the endpoints? F of 0? Yeah, 0 minus 2 cosine 0, which is -2. And f of 2 pi is 2 pi minus 2 cosine 2 pi, so 2 pi minus 2. even without a calculator, I claim that the absolute minimum is pretty easy to find. So which one is the absolute min? Is it the 7 pi 6 plus root 3, 11 pi 6 minus root 3, 2 pi minus 2, or the negative 2? And you can tell that all of the others are positive. Does that at least make sense? Like pi is 3-ish, right? So the last one's positive. The first one's obviously positive, right? And the second one, well, root 3 isn't bigger than 11 pi 6 because root 3 is somewhere between 1 and 2. And 11 pi 6 is almost 2 pi, right? So it's not that one. I do think, I said that the 7 pi 6 plus root 3 was the max, but I don't think it's totally obvious. I don't know if I actually calculated them to compare that or what I did. I don't think it's, so I would actually get decimals for the rest of them to compare. But still give the exact thing as your answer. Does that make sense? So this one's about 6.66. This one's about 4.02. And that one's about 4.2. So what's your absolute max is f of 7 pi 6 equals stuff. Is that okay? All right. All right, finding critical numbers involves finding the derivative, right? So on example 8, how about you use your favorite quotient rule to find the derivative? You can sing yourself a happy song. What? It's a happy song. And I think there's a Pop Goes the Weasel app for it.
Song.
Yeah. Low-de high, high-de low, over low squared.
Should we do math like they did it in The Simpsons? You know, how does this number make you feel?
The Simpsons is full of math, written by a bunch of math nerds.
Is the
Low-de
number 7
high
really odd, or
minus.
is it just misunderstood?
Oh, that's good. D low over low squared. Were you able to watch your negative signs correctly on your quotient rule? Did anybody else get 16x over x squared plus 4 squared?
Yeah.
Okay, great. So figure out where this thing is equal to 0 / undefined. So if you're solving that equal to 0, does the denominator matter? Because you just multiply by it and it goes away, right? By both sides. It'll be 16x equals 0. So one critical number is x equals 0. Okay. And is this derivative ever undefined? Does x squared plus 4 ever equal 0? No, this is not undefined either. Okay, so you have your one critical number. And so now what numbers are we going to plug into our function to test? 0. 4 and -4. And it's still on your page, but it's not on mine. So f of x was x squared minus 4 over x squared plus 4, right? Okay, so what does plugging in 0 give us? -4 over 4, which is -1. Plugging in 4, we get 16 minus 4 over 16 plus 4. And since you're in calculus, you can reduce your fractions. Yeah, most days, yes. 3/5. There we go. And when you plug in -4, you get the same thing. Now that's okay. This just means that the maximum happens at both endpoints. Okay, that's not a problem. The maximum value is 3/5. It just happens to occur twice. So f of 0 equals -1 is the absolute min. And f of 4 equals f of -4, which is 3/5. That's the absolute max. So don't be freaked out if you get like the maximum or the minimum occurring twice. It's not a problem. Especially because it just asks, the minimum and maximum really just means the y value as well, right? So this just tells you it happens in 2 locations, but I'm pretty sure the website, all it's going to want is the y. Like think about sine on the interval from, I don't know, -4 pi to 4 pi. What's sine's maximum going to be? What's sine's minimum going to be? And it's going to happen a whole bunch of times, right? So, you know. Okay. And then one more and we can go. This one, there's going to be critical numbers where the derivative is undefined as well. So I'd like you to find the derivative for this guy. I would first distribute and add powers. Okay, so try that. See if you can get the derivative correct. Okay, so if we call it all f of x's, that's going to be 8x to the 1/3 minus x to the how many thirds?
2/3.
I think 4/3.
Yeah,
Do you guys agree with 4/3? Okay,
I was doing it wrong.
it happens. Addition is tricky, especially when there's fractions. So what's the derivative now?
8/3.
To the negative 2/3 minus 4/3 x to the 1/3. Great. So let's simplify that. 8 over 3x to the 2/3 minus 4x to the 1/3 over 3. Which fraction needs something and what does it need?
The second one.
Second one needs x to the 2/3. So that's gonna be, and look, it works out nice, doesn't it? 8 minus 4x over 3x to the 2/3. Okay. So where is f prime of x undefined? At x equals 0. And if you actually solve it equal to 0, you get x. I don't think it's -1/2. I think it's 2. Do you get 2? Yeah. So f prime equals 0 at x equals 2. So you have 2 critical numbers. One of them happens to be your endpoint. It would have been more clever of me to make the interval -1 to 8. So you would have had to test more things. Okay, and then plug them in. So we're going to test f of 0, f of 2, and f of 8. using the function f of x equals cube root x. Is it 8 minus x or x minus 8?
8 minus x.
Thank you. And two of them are easy. What's f of 0? What's f of 8? 0. F of 2 is the cube root of 2 times 6. You have to know what that is to know it's the maximum, right? Because it's positive. So what's the absolute minimum? 0. Yep, f of 0 equals f of 8 equals 0. And the absolute max is f of 2 equals 6 cube roots of 2. It'd be super, super duper smart